First of all, thank you very much for the opportunity to present here a couple of fundamental state-of-the-art anticipated for the development of concerning lithium-ion batteries. Very grateful, especially also for those people joining virtually now and listening. So, I mean, if there's an urgent question, of course, you could ask it right away. Otherwise, I'll be happy to answer any question that you might have towards the end of the talk. Let me see. Sorry. Just a quick outline because it's a bit longer. So I will start with a very brief introduction, basically highlighting why we need the energy transition, and then make the link apparently to batteries and the importance of batteries for the energy transition and for a successful energy transition. Before then, I will introduce what lithium-ion batteries are, very few fundamentals basically. I mean, what is important to consider when talking about lithium-ion batteries and batteries in general, current research activities, and eventually finalize or conclude the talk with a brief summary. So just to start, something that I call the Y pyramid, basically. It's just terms that you're all familiar with, you've heard many times across different newspaper articles probably and whatever you came across. So why we need it, basically, just to put things in order, right? Because we have the climate change. And why do we have the climate change? Basically, because due to the continuous greenhouse gas emissions that have rise substantially in the past, and those we have because we're because of the combustion of the limited fossil fuels that we have and that we make use of, and those basically we have because we have an exponentially increasing energy demand worldwide. So, as said, nothing new basically, but putting things in an order. And concerning the last part, so the exponentially increasing energy demand worldwide, I'd like to show this little graph basically that is highlighting very nicely, in my opinion, the evolution. So you see that we have indeed a kind of exponential increase of energy consumption. And you see basically we have a very large share of coal, of course, right? Did not really matter earlier too much, basically oil and others, gas especially, and then I mean an increasing fraction also of renewables, together with the traditional biomass that did not change substantially, as you can see here. And I'd like to highlight two dates basically here. So one is 1950, more or less, where you see starting from then, basically we have a very sharp increase. So before that, basically the increase was rather, I mean, relatively speaking, negligible. And why am I highlighting 1950? Because 1950 might sound somehow long ago, but 1950 is pretty much 2 generations. So that's more or less the time when my parents were born. So, and you see, before that, basically, right, we were using only very limited, relatively speaking, very limited amount of oil, gas, and even coal, basically. So there has been an exponential increase since then, basically, since about 70 years. And the other date that I would like to highlight briefly is about 1900. So where you see where, I mean, it was not really, I mean, there was a slight increase, but nothing compared to the last 70 years, basically. So everybody was happy with coal, very tiny fraction of oil, as you can see here, and the traditional biomass. And I just go the pointer out. So, yeah. And why am I highlighting 1900? Because already at that time, so more or less, Wilhelm Oswald said, the path leading to the solution of the most difficult of all technological questions, I mean, not really difficult compared to what we're facing now, the delivery of cheap energy must be discovered by electrochemistry. And so it's particularly noteworthy because, as said, there was essentially very little increase and very little demand of energy compared to what we're facing today. But at that time already, so more than 100 years ago, he highlighted the importance of electrochemistry to address this issue. He won later on the Nobel Prize. And in fact, then it took another 110 years, basically, until there was another Nobel Prize in that field of electrochemistry, batteries, basically. I think don't have to be introduced. John Goodenough, Stan Whittingham, and Akira Yoshino, who were awarded the Nobel Prize in Chemistry 4 years ago. So when talking about the importance of electrochemistry and batteries, I'd like to stress also another point that is sometimes a bit overlooked, maybe because but less apparent in the newspapers. If you think about renewable energy sources like wind, basically, and solar, then the major storage technology, in fact, that is used today is pumped hydro. That has an overall share of about 95% and efficiency of about 80%. So it's, I think, pretty decent compared to other storage technologies. Maybe not to batteries, but to others. So meaning that really I mean, by far, largest fraction is stored in such big water sinks. So as I said, frequently forgotten, but cannot be highlighted sufficiently that we always talk about batteries and other technologies, but overlook this sometimes. Nonetheless, there's a need for also other storage technologies, because I mean, you can easily imagine that pumped hydro is not an option for mobile applications. I mean, not talking about smartphones or portable electronic devices in general, but also vehicles. Or in fact, kind of geographic areas where pumped hydro is not an option either, because it consumes a lot of space. You need to have the right geographic conditions, basically. It's something like a small island, for instance, or any kind of other very flat land, for instance. It's just not an option. So for such mobile and peripheric applications, we need alternative energy storage technologies, as for instance batteries, any kind of batteries, right? So I'm going to talk about lithium-ion batteries there, but there's many other as battery source. I mean, as also depicted here in the course of the seminar. This is true also apparently for smart homes, including then a small stationary battery, basically, which apparently, I mean, where pumped hydro or any other kind of gas turbine or is not flywheels or anything else is not an option either, right? So we need, let's say, for a range of different applications, we need a range of different storage technologies, and one important contribution certainly comes from batteries. So putting it here, let's say, a bit more in the center, so to make use and to benefit, beside the large fraction that is stored in pumped hydro and others of renewable energy sources, to eventually use this green energy in applications such as vehicles, portable electronics, and smart homes, we need a certain energy technology. I mean, batteries and batteries are playing a key role here. So that's why basically in the center, right? So kind of very fundamental pillar for the energy transition. This becomes even more obvious when looking at the sales and anticipated sales until 2030, more or less. There are apparently different graphs and different numbers existing in the literature, but the trend is more or less similar always. And so you can see this is here split by applications. And if you then take a closer look, you see that the largest fraction of the anticipated battery sales is considered to be for vehicles, right? So here highlighted in green, and then, however, you also see a continuous increase here, the grayish part highlighted in purple, for stationary storage, where there's a greater choice probably even for different battery technologies. Why is this so important for Europe? In fact, right now, by far greatest fraction of batteries is coming from Asian countries. But you see that also in Europe, it has been understood, meanwhile, that we need basically to produce batteries as well, just because of their great importance. So we cannot rely simply on countries that are pretty far away only. So this is a map put together by colleagues in Spain from CIC and Gigune about the European gigafactories. And you can see that, I mean, there's plenty of activities running already or planned by companies apparently coming from Asia, right, like CATL, LG, but also companies coming from Europe, like Northvolt, and then car makers that are planning to have their own facilities, basically. So you see, there's a lot of there's a lot of plans and activities going on. I'm not sure if all of these will eventually, let's say, be realized, but if one or two won't, then we will see certainly some others coming up. So this once again, sorry, highlights the important role of batteries for the energy transition. But to be really successful in this regard, we need to make the batteries better from the current state of the art, which means we have to make them more sustainable, more cost efficient. Usually these two things come along, fortunately. We have to improve performance, right? Driving range, fast charging when talking about vehicles. And we have to make them safer, which I think is fundamental for the use in any kind of application that is near to humans. So the question that might arise then is how to get there. This is a scheme of a state-of-the-art lithium-ion battery. So the negative electrode is basically graphite still. To some fraction now people are mixing a bit of silicon or understoichiometric silicon oxide in. I'll talk about this a little later. Then we have a liquid organic electrolyte, commonly a combination of cyclic organic carbonates and linear organic carbonates, and then some lithium salt like LiPF6, mostly still used. And then at the positive electrode or cathode use, we use lithium cobalt oxide still. So that was kind of this first cathode material and still is used in portable electronic devices frequently. Something that is abbreviated NMC or NCM frequently. So where part of the cobalt is replaced by nickel and manganese, or in fact not part anymore, but 90 or 95% frequently. So they are becoming nickel and richer now. And lithium iron phosphate. Lithium iron phosphate basically that is now dominating, especially in Asia, and vehicles that are produced in Asia basically and then shipped to Europe at some point. So this is basically the state of the art. Just a very quick excursion maybe to talk about the same things eventually. So what happens upon charge and discharge, and which step in fact comes first in such a battery cell. So if we think about the reactions at the electrodes, then we have, as said, I mean, we stick to graphite now, which is abbreviated here as C6. Then we have lithium-ion intercalation into the graphite structure, so in between the graphene layers that you can see here, upon charge, and upon discharge, basically the lithium ions move out again into the positive electrode. And apparently then at the positive electrode, let's take here lithium cobalt oxide as an example for simplicity reasons. So upon charge, right, we're de-intercalating lithium cations from the structure. And upon discharge, basically the reverse. So this is abbreviated here. And in lithium cobalt oxide, we can do this with about more or less 50% of the cobalt of the lithium in the structure. Before then, at some point, the structure tends to collapse. In fact, the structure tends to collapse because it's a kind of layered structure, just like graphite, so to say, which is a bit difficult to see here, maybe from the scheme. So let's take maybe another image for the structure, for the crystal structure of lithium cobalt oxide. So you see here the cobalt oxygen octahedra, right, as here also apparent in the legend. And then you have the lithium cations basically in between these layers. And then they can be reversibly intercalated and deintercalated. And let's say very qualitatively speaking, you can imagine that if you remove all the lithium here from this interlayer, then basically the structure might collapse. And apparently this collapse is irreversible. So that's what you want to avoid, apparently. Yeah, just once again, a little bigger for those of you watching on the small screen. So you can summarize these two, that upon charge, basically, right, the empty graphite, basically, and the fully filled lithium cobalt oxide are reacting to lithiated graphite or lithium intercalated graphite, and lithium cobalt oxide with a reduced amount of lithium in the structure. And upon discharge, then exactly the same. And this is basically the nice thing about these lithium-ion batteries, is that you just intercalate and deintercalate lithium cations from two-layered structures that are undergoing a few structural changes, but limited compared to other class of materials. And this is also, first, the reason why this is so reversible, so why we can charge and discharge lithium-ion batteries for 1,000 or 2 or whatever 1,000 times. And it's the other, let's say, reason why this in its early stages was also called rocking chair battery, right? Because it's kind of like a rocking chair, basically the lithium cations are migrating from one electrode to another, back and forth, back and forth. Another important aspect to when we talk about batteries in general, and when we talk about lithium-ion batteries, or in particular maybe, is how to talk. I mean, what eventually determines energy density or energy, specific energy, so per mass or per volume, because frequently scientific literature refers to capacity, and that's an important factor, but it's not the only thing. As you see here on the scheme, because so this is the discharge profile, right, for the cathode basically, and for the anode. So we have here the lithium loss, so you can see that the potential is going down, and for graphite basically, you have the lithium intercalation here, so the potential is going down, and for graphite basically it's the de-intercalation, so the potential is going up. And what is important in addition to capacity is the cell voltage, right? So the difference between cathode and anode, basically. And then the product of the cell voltage and the capacity is the energy. So meaning that we don't gain much if we just increase the capacity, but also increase the voltage. Or if we just reduce the voltage and basically shorten the capacity, and especially considering that, I mean, graphite is a wonderful material, right? So you see it's very close to 0 volts, so 0 versus lithium plus lithium, meaning that it's hard to get even lower than that, except if going for metallic lithium, while apparently we would need to increase the capacity at such low voltage to really make a great impact on the eventual energy. It also shows, though, that we can maybe potentially keep the capacity of the cathode constant, but just increase the cell voltage and then get a significant gain in energy. So this is important, I think, because frequently, as said, we're just talking about capacities and not about voltage or average voltage of a certain material. It's also important to highlight maybe briefly another point is you see here that we're talking about cell voltages, at least in the fully charged state, of about 4 volts, 4.2, 4 point something, which is clearly beyond the electrochemical stability of water, which is about 1.2 volts, meaning that if we would use an aqueous electrolyte here in such case, then we would form hydrogen and oxygen, basically. That's why also here the keyword electrolysis of water. So that's why people had to use an organic based electrolyte, right, with a higher electrochemical stability that basically allows for the combination of such materials which such a great cell voltage and potential difference. There was one big issue towards the development of lithium-ion batteries, though, that the electrochemical stability of common organic electrolytes is somehow limited, maybe not towards oxidation right here, or towards high potentials, but towards reduction, basically. So you see there is a little gap here to graphite. And in fact, this is was one of the biggest issue, one of the greater challenges probably towards the developments. Finding a solution for this, and I think we've been pretty lucky that by finding EC, basically when it's reduced, it forms a stable passivation layer on top of the graphite electrode, the so-called solid electrolyte interface, that eventually enabled kinetically stabilizing this interface, and so let's say making, not requiring any more thermodynamic stability of the electrolyte towards such low potentials. The SEI, I mean, is a term that is frequently used, and we know most of the components frequently, but it's still, let's say, not fully understood how it's working and how we can fine-tune. So electrolyte additives, for instance, that might have a positive effect on the stability of the SEI. It's still a kind of the search for such successful or efficient or effective additives is still a kind of trial and error chemistry frequently. So there have been approaches to, let's say, organize this a bit better, but still frequently people are trying different chemicals and seeing if it works or doesn't. Okay, so this was a bit, let's say, background. Let's get back to the state of the art in lithium-ion batteries. So that's the slide that you've seen already. And when talking about the potential improvement of such, I was mentioning sustainability, so, and potentially cost. This is largely about the positive electrode, about the cathode, I'd say. When talking about safety, you might easily imagine that these liquid organic solvents are very flammable. So it's largely about the electrolyte, and it's not only about the flammability of the solvents, but also about the reactivity of LiPF6, for instance, in combination with water forming HF, which is not only highly corrosive, but also generally toxic. And then when talking about performance, especially fast charging, then it's especially about the negative electrode, so about the graphite. And energy density as well, but I mean, that's apparently the sum of everything, as you've seen just a few slides ago. So starting from the state of the art, right? So this is a kind of very qualitative roadmap that we came up with together with major funding agencies in the US, China, Japan, Europe, Germany. That is depicted here. So the idea of this plot, let's say, is how to get from the current number of EVs to more EVs. So you see that this is kind of, as I said, very qualitative material development roadmap. And what I said on the previous slide, so when it's about improving energy and especially power density, then we need to think about other materials on the negative electrode. And the clear idea is to go from graphite to graphite silicon oxide or graphite silicon, which is, I think, increasingly, let's say, the state of the art, to silicon carbon composites, right, with an increasing fraction of silicon. And then ideally metallic lithium and or metallic lithium in so-called anode-free concepts or zero-access concepts, which I will introduce towards the end of this talk. If we think about safety, Then, as I said, this is largely about the electrolytes, so going from flammable liquid organic electrolytes to non-flammable liquid electrolytes, and then to potentially ionic liquids, and eventually to solid-state systems or quasi-solid-state systems, something that is having a certain fraction or a significant fraction of a solid component, and generally provides greater safety in terms of less or ideally non-flammability, and other important factors. So that's roughly the idea, and I mean, there's been a lot of newspaper and press releases about companies that are starting with these solid electrolytes, and it's kind of interesting to see that none of them right now, I mean, most of them are working at least now with so-called hybrid systems, right, where they combine different electrolyte components to yield the performance that we eventually need. And when talking about greater sustainability, as I said, this is largely about the positive electrodes. So we have here LFP, which is quite sustainable already, but would benefit from some boost in energy density. And then we have NMC, the different kinds here. So that means it's about an increasing nickel fraction, especially a decreasing cobalt fraction. And then eventually it would be, the target is to have manganese-rich cathode materials, since manganese is much more abundant than nickel even, and less costly. The other target is to use water as the processing solvent during the electrode fabrication, and I will talk about this a little later. Another, and I think cannot be highlighted sufficiently, important aspect towards greater sustainability is recycling. Recycling and reuse as kind of direct recycling. And it's not only important in terms of the components that we have in the battery to make sure that we don't lose them, and let's say for ecological reasons, but also for economic reasons. In fact, Europe, Germany is, I mean, just one example. We're not very rich in resources that we need for batteries, basically. So importing batteries is somehow a way to import such elements, such materials, and such components. So by let's say just wasting or trashing them, I mean we waste, I mean, a lot of valuable materials and components. So by recycling them, basically, that's also for strategic reasons, I think, especially for Europe. I think it's quite important that we're not importing only batteries, but also materials that are considered critical. And so by an efficient recycling, basically, we can make use of these. And I'll talk a bit later about the direct recycling of battery materials. So as said, when it's about the negative electrode, it's about faster charging and higher energy density. So we might briefly think about why fast charging is limited and why this is specifically limited, I mean, related to the negative electrode. As you've seen in earlier, graphite is a wonderful material because it operates at such low potential. But the drawback, I mean, nothing good comes without the drawback, basically. The drawback of this is that it's very close, as said, to the redox potential of lithium. So when we apply fast, high currents, so fast charging, or we do this at low temperatures, then we risk that we plate metallic lithium here, as depicted here, on top of the graphite electrode. And that has an impact on what I mentioned earlier, the SEI, right, the solid electrolyte interface, because we continuously then, in such case, decompose electrolyte at the interface between the negative electrode and the electrolyte, which is an issue for faster aging. But it also poses the risk if this metallic lithium deposits in so-called dendritic structures. And these dendrites then grow through the separator that is physically separating the anode, sorry, the anode and cathode. then it might result in a short circuit as schematized here, basically. And this short circuit might result in a thermal runaway, and then eventually, in worst case, a fire, basically, of the battery cell. I mean, this is not a real fire, as you can see, so this is a kind of animation, but that's the risk that we're facing. So we need to develop new materials with potentially faster lithiation properties if we want to realize battery cells that are really able to be very rapidly charged, which is not an issue for mobile phones, for instance, right? But it's an issue for electric vehicles, especially. And when thinking about potential alternatives to graphite, then there's more or less three classes of alternatives. So graphite as a classic intercalation material, right? So a kind of two-dimensional structure, or two-dimensional structure with planes basically stacked on top of each other. Then we have kind of insertion type materials where the lithium pathways, let's say, are one-dimensional or three-dimensional. We have so-called conversion type materials, which out of these three is probably the most recent one, discovered in 2000, that this process might be reversible. So commonly transition metal oxides that are then, upon reaction with lithium, basically reduced to the metallic state, so the transition metal, and then embedded in some matrix of lithium oxide. And then the maybe even oldest, let's say, alternative are alloying materials. So elements, metals, metalloids that can electrochemically alloy with lithium, and then basically reversibly release also these lithium cations after the alloying process. And this is what I'm going to talk about briefly now in the following, because it's currently, let's say, from industry, the way to go. So this is you see it's a plot, right, of the gravimetric capacity in milliampere hours per gram versus the volumetric capacity in terms of ampere hours per liter. And so here you see graphite. This is not an alloying material, as I said, right, but just as a reference. And you can see that if we go to zinc, for instance, or aluminum, we would largely benefit in terms of volumetric capacity, but also in terms of gravimetric capacity. And if we then further would go to lead, which is maybe not really an option because it's toxic, and tin, which might be an option, but maybe not at the for the everyday battery, basically, because it's also not, I mean, also not that abundant and rather costly. And you see that here, by going to magnesium, that would be a big step already, right? And magnesium is much more abundant, but its reactivity with lithium is a bit more complex. So fortunately, something that is even better, so to say, is silicon, and silicon is very abundant. And the alloying process is very reversible in general. So this is basically the target, right? So go from graphite to silicon. And there are, however, a couple of issues along the way. So you've seen on the previous slide already that this alloying reaction comes along with a big volume expansion. And so once, I mean, upon lithiation, it's an expansion, right? But upon delithiation, it's shrinking again. So we have a very high, I mean, very extensive volume changes, which means a lot of stress basically on the particle. So frequently, if the particles are too big, we're facing pulverization issues that are depicted here, basically. And the stress apparently is not only at the particle level, but also at the electrode level, then potentially resulting in delamination issues and electrically or electronically isolated particles that are not then available anymore for any further lithiation and delithiation reaction. So initially and at present, the major strategy is to go for some kind of composite, right, with graphite or any sort of carbon, basically, where you try to buffer these volume changes and the potential loss of electronic contact by embedding this in whatever kind of carbon matrix. That's kind of the state of the art, I would say, in high energy lithium-ion batteries. But the clear target is to go from graphite to basically some sort of only silicon-based electrodes, which is apparently more a much greater challenge owing to the hurdles, the technical hurdles that I mentioned earlier. Nonetheless, right, this is the ultimate goal. So there is a lot of people working on this. And one example is here. So this is, you can see, right, it's micro-sized silicon particles. Why micro-sized? Because it's just a cost issue, right? Any kind of nanoparticles basically are difficult to handle and eventually expensive. So, and cost is apparently a major driving factor. So ideally, it's about micro-sized silicon. And you can see, I mean, this is just a lab example apparently, right? But you can, and so-called half cells, so with the lithium metal counter electrode. But you can see that these lithiation and delithiation process, especially if limited somehow, is very reversible, right? So even for these micro-sized particles, so there is, I would say, a reasonable hope that we can have the transition from graphite to such silicon particles also in industrial sales eventually. So still at the beginning, I would say, but a kind of pretty promising pathway. Having said, talking about cathode materials, right, sustainability, then as said, it's largely about removing cobalt from the cathode, then ideally in the second step also decreasing the amount of nickel that we need. And it's about the aqueous processing of such materials. In fact, that's not only a sustainability issue, but it's also a cost issue. So this is schematized the electrode fabrication process. So you can see here that at the very beginning, I would just call it mixing, but it's quite, I mean, it's important, right, which components, like in cooking, basically, it's important which component comes first. And but generally, we provide the active material, the conductive carbon, a certain solvent, right, and the binder, and then we mix everything together, basically. And in the case of N-methyl pyrrolidine, the state of the art for the cathode, basically, because it's dissolving very nicely polyvinylidene difluoride, so PVDF. But NMP and PVDF as PFAS compound is apparently not the material that we would really like to use. In fact, so after the mixing and the coating process, we have the drying step, and you can easily imagine that, I mean, NMP, we cannot just dry and evaporate, so we have to carefully recover the solvents to be able to avoid any kind of exposure to the workers. And then basically we have the further processing by calandering, cutting, and notching. If we could replace NMP by water, then a lot of things would get easier. So this would basically remain the same, right? But here during the drying, we would not need to recover the solvent because, I mean, we can, of course, we can recover the water, but exposing workers to water vapor, if the temperature is not too hot, is not a big issue. So, I mean, it's not toxic or in any way. So that step basically is quite energy intensive and costly. So we could skip this basically, and even the drying we could go much faster basically. So we would save a lot of energy, and we thus basically a lot of cost if we could switch from NMP to water. But there's a reason why it's not done yet, and this is that all these NMC type and lithium transition metal oxides, they're very sensitive towards water. So as soon as they get in contact with water, you observe lithium leaching out of the structure of the cathode material, which is then in presence of water resulting in hydroxide formation. And this hydroxide these hydroxide anions basically then tend to attack the aluminum current collector that is used for the positive electrode, and then leading to this, as depicted here, right, to this pitting corrosion. And that's a big issue. The other point apparently is when we're leaching lithium out of the structure, then we have changes of the material, largely at the surface, but potentially reaching into the bulk. That is apparently an issue as well, right? So we're not only affecting the aluminum current collector by corroding it, but we're also degrading the material to some extent. And I will talk about this exemplarily for lithium nickel manganese oxide, or abbreviated LNMO, as a manganese-rich and nickel, let's say, relatively poor potential cathode material that I think is increasingly investigated now to become the next generation cathode material. So we did in this experiment a very extensive comparison of lithium nickel manganese oxide that was not exposed to any kind of solvent, right? So this is called reference. Then lithium nickel manganese oxide that was exposed to water. And then lithium nickel manganese oxide that was exposed to an aqueous solution of phosphoric acid, so PA. And so for LNMO at least, this is different for NMC type materials, but for LNMO, we did not observe, I mean, we did a lot of characterization techniques, basically X-ray absorption spectroscopy, we did Raman spectroscopy, we did X-ray diffraction, neutron diffraction. And you could hardly spot really any impact on the bulk of the material. But when you went to more surface sensitive techniques like high resolution transmission electron microscopy, for instance, or XPS, then what we've seen here in the case of water and in the case of phosphoric acid is the formation of a very thin, I mean, really nanometer, less than a nanometer, basically. Very thin amorphous layer here on top of the material. And we observe a reduction of manganese here in 4+ basically in the reference to 2+ in case of contact with water and 3+ in contact with phosphoric acid. And then to be fair, we processed all these materials with NMP and PVDF into electrodes. Sorry, the reactivity, right, remains limited to the surface area apparently. But we processed these into electrodes with NMP and PVDF, as also briefly mentioned here. And then you can see the difference there, right? So the bulk might not be affected, and the surface, let's say, effect might be very, very limited in terms of thickness. But still you see a significant effect on the cycling performance. So you see that the reference here in gray, right, is performing pretty well, I'd say. I mean, this is 500 cycles. And the material that got in contact with water before then being processed the same way as the reference shows a greater fading. So I need to highlight that, I mean, this is, let's say, rather large resolution, right? So we're talking here about the difference after 500 cycles of maybe 5 milliampere hours per gram. So that's not, I mean, that's not substantial maybe, but it's still, I mean, is significant. And we can prevent this nicely by adding this phosphoric acid, as you can see here in yellow, right? So, which is even outperforming the reference material. But in fact, other techniques then showed that there's a very thin metal phosphate layer basically on top of the electrodes. So that has apparently a stabilizing effect. So the interface and the surface, right, is the reactivity of the material with water is very limited to some extent, but this very limited reactivity has an important impact if we think of it in the long run, right? 500 cycles, and then you can easily imagine, I mean, it's a kind of linear behavior, what happens after the 1,000, 2,000 cycles. So it becomes significant in the long run. Another important aspect that people are working on is particle design, right? So Because once again here, the example of lithium nickel manganese oxide, but it's the same basically for other cathode materials. These particles basically have different surface faces with different properties. So this here, for instance, this purely octahedral shape, for instance, is covered with only 111 surfaces. And here we kind of truncate, right, part of these edges in such materials. And when we do a comparison of these two materials in terms of, processed into electrodes and then cycled, here for more than 500 cycles, basically, you can see that if we have these 100 truncated surfaces, so to say, then we have a better rate capability, in fact, because lithium-ion diffusion and charge transfer basically across these surfaces is supposed to be favored. But we can, with these purely 111 basically surface faces, we can improve cycling stability, right, as you can see here. So capacity retention, where we have 95% versus 90% for this truncated material. So you see, it's quite complex basically to not just synthesize these materials, but really to design the particles to a level where we can optimize performance quite significantly. Mentioned earlier, right, recycling is another way apparently to potentially improve sustainability of batteries. And this apparently can be done for all the components. I mean, the recycling of the current collector, copper at the negative electrode, aluminum at the positive electrode is relatively simple, I may say. But if you have a lithium transition metal oxide like nickel, cobalt, manganese oxide, it's a bit more difficult also already to recover the different elements. And we're talking about graphite. It's apparently an issue as well because any kind of high temperature treatment under oxygen, right, would just burn off basically all the graphite. So in addition to, I think, the great progress that has been made in terms of recycling, getting back the elements and then getting these elements back into materials, is the direct recycling. So where we don't go back to all the elements basically, but we recover the particles, so to say, right, and reuse these particles right away. And there has been quite a few activities already on for the positive electrode, and very limited, in fact, for the negative electrode. But that's why I'd like to show one example here for the direct recovery of graphite from spent lithium-ion battery cells. So this was a collaboration with the Helmholtz Center in Dresden-Rossendorf, which basically who developed this process for the recycling. So you can, together with an industrial partner, MSA. So they use really spent lithium-ion batteries, right, commercial battery cells. And so then basically they recover these, I mean, by, or recycle these basically in a multi-step process. And I will not go through all the details here. But what I would like to highlight is basically three things. So in the so-called black mass fine fraction, which contains all the active materials basically, we have about almost 99% of the graphite particles end up in there. So we have a very limited loss of graphite at this stage basically. Then there's a fourth rotation step where basically the active materials of the positive electrode and the negative electrode are separated, right? And then there's a chemical purification of the graphite to remove these minor traces, right, of transition metals and transition metal oxides that are depicted here in blue. And then we have the recycled graphite product. And so the recycling rate for this is more than 88%. Which I think is still pretty high, especially if you compare that. Otherwise, you just burn it, right, 100%. So then you end up with 0%. So 88%. Anything higher than 0 is high, basically, right? But to make it cost efficient, I mean, you have to approach apparently as high as possible values. But I think 88% is quite remarkable. And then our task basically was to test these materials and see if they are still working properly. So if the graphite material from spent lithium-ion batteries directly reused, so to say, after the recycling, after the purification process. And so we did a couple of comprehensive investigation. I will just show the results for the full cells here. So mixed with an NMC, combined with an NMC 532, so 50% nickel, 30% manganese, 20% cobalt, as active material for the positive electrode. And you can see that those cells, right, it's 3 times the same combination, so just for reproducibility reasons. So these cells are cycling pretty stably for 1,000 cycles and in effect more. Right? So you can see here, I mean, after 1,000 cycles, we have about 80% capacity retention, which is usually considered the end-of-life criterion. So that's at least comparable, in fact, with the performance as what we got for pristine graphite materials, depending on the supplier, I may say. So the recycled graphite was clearly better than some, very comparable with others, and maybe a little less performant with a few very, let's say, high performance graphites. So, but generally, I think the results are very promising, and in fact, we developed a few further, let's say, optimization process, which can really get it up to even the level of very high performance graphite materials in the pristine state. Last but not least, talking about safety, I think, as said, a major major factor towards the successful commercialization of batteries in any application close to the human body. And so one possibility to, as mentioned before, right, so we can go to non-flammable liquids, such as ionic liquids. We can go to solid inorganic electrolytes, like oxides, sulfides, or gerasides. And a major role basically is played by polymer-based electrolyte systems. In fact, this, just like other solid electrolyte systems, is supposed to be the most promising path towards lithium metal negative electrodes, potentially. So by this, right, further increasing potentially the energy density of the battery cell. In fact, I'm mentioning polymers also because lithium metal battery cells, or let's say the only commercial lithium metal battery cell today, contains a polymer electrolyte. And it's been used in the smaller vehicles, like right here, the Bolloré Blue car. But it's also been used in buses like the Citaro, basically from Daimler. So, in a sense, very successful. But the question might come up: why this has been so far limited to car sharing programs and buses, basically? And one possible answer, or one I think likely answer, is that we need elevated temperatures, so about 50 to 80 degrees C, basically, upon operation, so upon driving. But that would be, let's say, feasible somehow, right? I mean, once you're driving anyway, you have a certain heat that is released, basically, so that helps to maintain the temperature of the battery. So, but you also need this temperature upon charging, and this, I think, is the greater issue if you consider private vehicles, because anytime you would like to charge your car, right, the battery would have to spend a certain amount of its energy to heat up itself. And that's a bit more complex. So nonetheless, this is, as said, the only commercial lithium metal battery so far, rechargeable lithium metal battery. And the basis of the electrolyte in this case is a polyethylene oxide, or abbreviated PO, basically. A very simple polymer, I may say, quite cheap. And then there's a lithium salt added, such as lithium TFSI. And so this system, apparently the commercial systems are a bit more complex, but it's basically based on these two components. And then you see here, right, the conductivity as a function of temperature. So you have reasonable conductivities around 10 to the minus 30 siemens per centimeter, around 60 to 90 degrees C. So where the polymer is entering the liquidus range. And then basically here, once it's getting solid, it's dropping, right? And it's dropping to a level basically where it's not really useful anymore in commercial battery cells. So one potential alternative that we and others are working on are so-called single-ion conducting polymer electrolytes. So the idea here is that we do not have to add a salt, like lithium TFSI, LiPF6, or any other, but the polymer as such contains the lithium cation. So we covalently tether the anionic group basically to the polymer backbone as depicted here, and then we have the lithium cation. In fact, the only species or charged species that eventually then is mobile in such systems is the lithium cation. And so this theoretically provides the great benefit of that we don't have any lithium concentration gradient being built up, right? So different from the so-called, the PO with the lithium salt, where the anions move to the positively charged electrode and the cations move to the negatively charged electrodes, preferably. This we can avoid, right? Because the anion is fixed, and due to charge balance reasons, basically, the cation cannot just move away from the anion and leave it behind. So, and this, in return, so this absence of concentration gradients towards the electrode surfaces results, theoretically at least, in the absence of dendrite formation. So that's a great promise. And in fact, what we frequently see is indeed a more homogeneous lithium deposition. But there are two major challenges related to these systems, which are limited ionic conductivity, because you basically mentioned it's less mobile than when the anionic species is contributing as well. And we have a limited stability towards oxidation. This is not an issue only for single-ion conducting polymer electrolytes, but for polymer electrolytes in general. So also the PO mentioned earlier still is basically limited to the combination with lithium iron phosphate, because the threshold is more or less 4 volts. So above 4 volts, it's oxidized. So LFP at lithium iron phosphate with about 3.6 volts is kind of safe. And I'd like to just basically show one example here of such single-ion conducting polymer electrolytes. It's a bit more complex, let's say, the polymer architecture. So it's a so-called multi-block copolymer. So you see here the hydrophobic block that we added. So the hydrophobic block plays the role of, let's say, providing sufficient or suitable mechanical properties, right, with its high glass transition temperature. And we need these properties basically to get self-sending membranes, so polymer membranes that we can easily process. We stabilize the ether bond here in these systems, which is the critical point for the oxidation at elevated potentials, by these perfluorinated phenyl groups, basically, that have an electron withdrawing effect on the electrons here in the ether type oxygen, and by this basically stabilize it towards oxidation. And then we have an ionophilic block here in light blue, containing the ionic functions, right? So the anion covalently tethered to the backbone, and then the lithium cation with it, basically that apparently we need for lithium conductivity. And then to overcome the issue of the limited conductivity mentioned on the previous slide for PO, basically, we incorporate small molecules that are also frequently used in liquid electrolytes, such as here propylene carbonate. And the idea is that, these molecules need to have a high dielectric constant, right? Because then they can selectively coordinate the lithium cations. And by this basically, serving as, we call them molecular transporter. So serving as a kind of transporter to help the lithium cation to jump from one anionic site to another by several effects, right? Reducing somehow the activation energy that is needed by coordinating the lithium cation basically, and then helping to jump. But somehow, of course, also improving mobility, right? Because a coordinated lithium cation can apparently move easier than a naked, so to say. And then, of course, in addition, these coordinating small molecules in the ionic domains improve the mobility of the side chain, right? And then basically by just some sort of statistics improve, let's say, reduce the time that is needed that two side chains are sufficiently close to each other so that the jump gets possible. So they play certain, several roles, so to say, but as said, the high dielectric constant is important so that they can nicely coordinate the lithium. And then we can decouple to some extent conductivity, right, and so the polymer dynamics. And this is here the system at a glance, basically. So let's assume we have a lithium metal electrode here, right, and the lithium nickel cobalt manganese oxide here at the positive electrode. And then in green here is the ionophilic domain. So these polymers, these block copolymers tend to separate into domains, ionophilic here in green and ionophobic here in blue, which, as said, gives us the right combination of mechanical properties and electrochemical properties. And then you can see here in this magnification, basically the preferred coordination of the lithium, of the ionophilic domains, and specifically apparently the lithium cations, by these solvent molecules. Here EC, so ethylene carbonate, but as said, anything that with a high dielectric constant works well, basically. And then with these systems, we can get very stable cycling, right, at a rather high C rate of 1C. And I think maybe even more remarkable is that this test has been conducted at 20 degrees C, and it uses an NMC 811 cathode with an elevated cutoff potential, basically, of 4.3 volts. So something that would not have been possible, neither the high rate cycling, nor the 20 degrees C, nor the NMC 811, basically, with PO. And in fact, the system even works well at 0 degrees C. So just wanted to highlight that we have already lithium metal batteries in place, right, commercially available, but there is need for improvement. And there are a couple of approaches. Not only this system, but many, I think, polymer systems that potentially offer improved performance. Nonetheless, as mentioned earlier, there is no advantage coming without a drawback. So you might easily imagine that, these complex molecules, polymers, the synthesis is a bit more, let's say, complex than synthesizing polyethylene oxide. So, yeah, but I think it's showing the potential of a smart polymer design to really then get high performance batteries that can be used at room temperature and below and still show great performance. So having said this, talking about polymer electrolytes in combination with lithium metal electrodes, right, and NMC type cathodes, for instance. So having a, let's say, more global perspective on the system, you see that we have a big excess of lithium, right? So because in a lithium-ion battery, where this instead of lithium metal would be graphite, the only lithium source would be the positive electrode. And here we have the lithium source, the positive electrode as lithium source, and we have plenty of lithium at the negative electrode. So people thought about, I think it's about, not yet 20 years ago, but people thought potentially we could remove the lithium metal and then have a kind of lithium-ion battery, in the sense that basically the only lithium source is the positive electrode, but it's still apparently a lithium metal battery because it would be plated as lithium metal on the negative electrode. Yeah, basically, let's say on the current collector, naked or modified. So this is then referred to frequently as anode free, which is not fully correct apparently, because I mean there is no battery cell without anode and cathode, or a zero excess lithium metal battery, right? Which I think maybe is a bit more precise, let's say, because it's a lithium metal battery in the charged state, right? And but we don't have any excess lithium metal, any excess lithium as when we put a lithium metal for it. And in fact, such systems, there have been a couple of very nice papers on such systems, basically showing the potential that you can cycle such cells for hundreds and maybe even 1,000 times, basically. So you see here that basically is the evolution in terms of time, right, versus energy density in terms of watt-hours per kilogram. And you see that practical lithium-ion batteries, they continuously increased their energy, the energy density continuously increased. I think that's also something that is worthy to be highlighted, right? I mean, in average, I think we had like 10% increase every year. And I think that's a very remarkable value, not only to materials, I mean, largely to engineering. But anyhow, I mean, the two have to work together anyways. And then you see, so this is commercial values, right? So industry values, so to say, and everything above here, this dashed line, which is considered to be the present commercial lithium-ion battery, is apparently literature values, right? So from scientific labs. But you see here that by transitioning from lithium-ion to lithium metal, basically, and then to these so-called zero-excess systems, right, which is abbreviated here as Cu for copper. So there is no lithium metal at the negative electrode to start with, only a copper current collector. And then, I mean, the work that was reported here in this paper, you see that there is still a lot of room for improvement, right, in terms of energy density. So I think that's another important message, is the story of lithium batteries, lithium-ion, but also then lithium metal batteries is probably still to be told to its full extent. Nonetheless, I mean, having talked about lithium batteries now, I'd like to, let's say, briefly point out that, of course, lithium-ion batteries, the costs have been decreasing continuously over the years, but there has been a sharp increase when basically Russia attacked the Ukraine, and there was a sharp increase in price of the lithium carbonate that is used for making lithium-ion battery materials. And then apparently also that was the first time that the price of lithium-ion batteries increased a little again. And now, I mean, it's relaxing a little, but the cost of resources are apparently important. And it's not only about the cost, but strategically speaking, it's also about their availability and abundance. And this is not only true for lithium, but even more so for cobalt, of course. Which means there are some criticality concerns about the different components. And this, I think, has been nicely addressed then by the recent announcements concerning the development and commercialization of sodium-ion batteries. And I will not talk about this further, but I would like to make some advertisement for the seminar for next week that will be provided by Stefano Passerini, and in fact on sodium and other post-lithium batteries, where he will explain this in much more detail. And I think a very important aspect. So lithium-ion batteries are certainly great, but I think it's important that we also work on alternatives. Having said this, basically, I'd like to conclude. So just very briefly, right, I think lithium-ion batteries will remain the energy storage technology of choice for portable electronics, and especially EVs, for the next 10 to 15 years, simply because they have the highest energy density that we can think of right now, to be followed up eventually, probably, presumably, by lithium metal batteries. employing a solid state electrolyte or any kind of hybrid system, maybe even a liquid, let's see, that promise much higher energy densities, especially in the so-called zero access concept, right? If the remaining challenges such as cost, scalability, and performance will be successfully handled also at the large scale. But generally, I mean, you've seen this for lithium-ion batteries. We have a great, I think, selection of active materials, electrolyte systems that we can use. I mean, solid state, we have polymers, you have inorganic solids, oxides, sulfides. You have the wide range of liquid electrolytes, right? And on the negative electrode, you have graphite, you have silicon, you have other alternatives that I did not mention now. Like lithium titanium oxide, you have lithium iron phosphate at the positive electrode, you have these lithium nickel manganese or cobalt oxides, you have lithium nickel manganese oxides, right? So there's a great variety, which is apparently getting even greater if we think about not only lithium-ion battery systems or lithium battery systems, but also sodium and other alternatives such as potassium or magnesium, for instance. And I think the diversification is in any case beneficial with regard to ecology, right, economy and geopolitics, because it just helps to establish basically other technologies that might be more suitable for specific applications for whatever reason eventually. And having said this, basically, I also believe that there is still a lot of improvement. You've seen this 10% increase in energy density, right? But there's also, I think, a lot of room still for improvement to make batteries more sustainable, cost efficient, and eventually safer, and of course, further increase energy and power density. So I think there is still a lot to do, and but that's also for us it's great, of course, because there is still a lot to do. So having said, and with this, I'd like to thank all my former and present group members. Basically, a large fraction of them is shown here on this photo. All the national and international partners, so all the work we did. Apparently, we did not do alone, right? We're always together with others, mostly. Supported by a range of different public funding institutions, but also private industry. And of course, you very much for your kind attention, and I would be very happy to answer any question that you might have. Thank you. If there is any question. Ah, there is one. Yeah? I've seen that Zachariah Fuentes, if I got it right, raised the hand. I may say that I don't see the chat, so in the current view. So if there's a question in the chat, it would be great if.
So far, we've not received any. Oh, we have a question. I will read the question. It says, how does the fluorinated phenyl group affect the oxidative stability of SIPE, SIPE? Yeah. What is the principle?
That's a very nice question. Which, indeed, I mean, this is a very nice question because it was a question that we asked ourselves as well. It plays a very important role. I mean, you can synthesize the molecule also without the fluorine here in the backbone. And so I mentioned already that it increases the electron withdrawing effect here on the ether type oxygen, right? And this, in fact, if you synthesize the same molecule without the fluorine here, basically, what you observe is that the electrochemical stability towards oxidation is decreasing because the electron withdrawing effect of this perfluorinated phenol compared to the pure phenol, so to say, is much higher. So the electron density here in the oxygen is higher if there's no fluorine in here, meaning that it's more easily oxidized. So you see this in terms of electrochemistry towards oxidation. The fluorine here in the backbone, however, does also play a role for the reactivity with the lithium metal. In the sense that if you have the fluorine here in the backbone, you form a very, lithium fluoride rich solid electrolyte interface in contact with the lithium metal. If you don't have the fluorine here, you don't have this LiF formation basically, or to much lesser extent, and you see this basically in a reduced stability of the polymer in contact with the lithium metal, and then basically shortened cycle life or increasing polarization. So it's important for both, right? So the stability towards oxidation, thermodynamically, so to say, and kinetically towards reduction by forming a lithium fluorine-rich interlayer. So it's super positive, performance-wise, behavior-wise, but it's apparently not super positive in terms of cost and all the discussion that we have about PFAS. So that's something that, we kind of published rather recently the impact, but that we're working on right now is to replace fluorine by the other options somehow in order to maybe in the first step reduce the amount of fluorine that we need, and then ideally, of course, in the long run, get rid of fluorine in the electrolyte. But as you've seen, it's not an issue only for the polymers, it's also for the liquids with the LiPF6 with having a very high fluorine concentration. So I think we'll see, but that's going to be one of the toughest questions to make lithium batteries fluorine free. Not easy. At least if we want to reach the same energy density, power density, whatever, that we have right now. So I hope this answered the question.
We have another question. I read, what is your opinion of using lithium-ion conducting electrolyte in electrolyte?
Okay. I'm not sure I fully understand the question.
Thermic based?
Okay, sorry. Okay, I missed this part.
Yes, it was just added now.
Okay, thank you. Okay, no, okay. Yes, there is, as there are companies working on polymers, there are companies working on ceramic-based solid-state electrolytes. As I said, there is no system that is only advantages, and there is no system that is basically only suffers from any kind of disadvantages. When thinking about ionic conductivity, then sulfidic type electrolytes, agirodite, certainly are ahead. When thinking about stability in contact with the lithium metal, but potentially also in contact with oxidation, then these sulfidic or agirodite type electrolytes are usually showing a rather narrow stability window, even much narrower than the polymers. While differently, the oxides, also inorganic oxide based solid state electrolytes, they usually show very high electrochemical stability. but they suffer generally, of course, from relatively lower ionic conductivity, and especially, let's say, it's a bit harder to process them because of their rigidity. That's why, I mean, for a long time there has been, let's say, the either/or question, either sulfides or oxides or polymers. I think apart from the fact that, of course, all these materials are very rich in terms of composition that you can achieve with all the different properties that would result then from these different compositions. You see, as very briefly mentioned during the talk or during the seminar, you see that most of the companies that were focusing on one component now are combining different components to benefit ideally from all the different advantages that each of these systems has. So that's why I think it's not unlikely that any kind of eventually successful system, and that might be different ones. So there might be like it is right now, right? So we might have different electrolyte systems that will be commercially successful. It's not unlikely, let's say, that one or many or all of these eventually commercially successful systems will be a combination of a ceramic phase, of a polymer, and potentially even some sort of liquid phase. Because of, I mean, yeah, I mean, there's the only goal is to make batteries better, to reach better performance, high energy density, and make them safer and more sustainable. So whatever is going to be inside eventually. And I think the smart combination of different components probably is the key. I mean, is a very promising way to go. So I did not talk about this here because it's not our major focus. So there are other people probably having much greater expertise. But yeah, I think each of these systems deserves to be further developed, better understood, and then potentially combined by different groups and institutions collaborating on these systems.
I read the next question. What was the impact of phosphoric acid on LNMO to boost the cycle performance? From the pictures, it seems that the reference looks better than PA modified LNMO on surface.
Okay, maybe there was a misunderstanding because the PA stands for phosphoric acid. Okay, but I will briefly anyway. So maybe just briefly once again. So if we bring the LNMO in contact with water, then what we observe is this formation of this very thin amorphous layer, right? And we see that the manganese at the surface, not in the bulk, but at the surface, is reduced basically from 4+ to 2+. In fact, when we did I did not mention, but when we did the neutron diffraction, we're also checking the reactivity not only with the water, but also with deuterated water. And we observed that there is probably to some minor exchange, minor fraction, basically, there is a, what is frequently for NMC type materials reported is this kind of lithium proton exchange. In that case, a lithium deuterium exchange. In the case of the phosphoric acid, what probably happens first due to the greater reactivity is that the phosphoric acid reacts with the lithium transition metal oxide and forming a thin layer of probably predominantly lithium phosphate, potentially also some manganese phosphate, and to a lesser extent nickel phosphate here at the surface. And this metal phosphate layer then stabilizes the interface, right? And so this is then shown here in yellow. So when you use phosphoric acid, aqueous phosphoric acid instead of water, you still have a reaction, but this reaction has a positive impact on the cycling stability. I should add that this lithium nickel manganese oxide, right, operates at 4.7 volts more or less. So we charge the cell to about 5 volts, 4.9, meaning that we have potentially a lot of electrolyte oxidation. And this metal phosphate layer plays a similar role, let's say, as the Se-ion graphite. So it's kind of kinetically stabilizing the electrolyte at the interface. And that's why the slightly superior performance compared to the reference material that was not in contact with any water. I should add that if you don't only treat the material with the phosphoric acid and then process everything with NMP and PVDF, as done here for comparability reasons, but if you use water and phosphoric acid for the electrode preparation, right, then with another binder than PVDF, then another positive impact of the phosphoric acid is that, in fact, it forms an aluminum phosphate layer on top of the aluminum current collector, and then prevents the pitting corrosion that I was showing here. Right? So the phosphoric acid can play different roles depending on how basically exactly the electrode preparation process looks like. And it turned out generally beneficial to add this. You can maybe just in case the question went in that direction, you can somehow get a similar result or comparable results by, instead of treating the material with phosphoric acid, right, and then having the formation of this metal phosphate layer kind of in situ. I don't know how you, I mean, basically forming it, right? You can, of course, also form a lithium phosphate layer or transition metal phosphate layer as such artificially. So in absence of phosphoric acid, and those metal phosphate layers also have a beneficial effect. I mean, there's a bunch of papers showing this for the different phosphates, basically one working better than the other. But I think here, I mean, what is difficult in such cases apparently is to get to such thin layers, right? So usually then we're talking about 2 or 3 nanometers, maybe more or less. I mean, and so, but also this turned out beneficial. So let's say generally any kind of very thin metal phosphate layer that you can deposit probably on these particles has a beneficial effect if properly done. But phosphoric acid just does the same trick. Is there any other question?
So far, no other questions.
No further questions? Should we close it then, or?
Yes, I would suggest so, except if Linda would like to add anything else.
Can you hear me?
Yes.
Okay. Now, I want only to thank you for the great seminar. And I had the opportunity to attend this seminar, and it was very interesting from my side. Thank you again.
Thank you, Linda. Once again, also thank you very much from my side to you, Linda, for the possibility to present this year. To Adiola, of course, for the great support during the preparation and all the technical support today, and anybody who has been joining and listening, and the active participation at the end. So thank you very much appreciated.